Good morning, everybody. I hope everybody had a wonderful weekend. Just kind of getting organized here a little bit. I should probably make sure that I'm not running an upload in the background. Give me a moment here. All right. Sorry about that. I was uploading something in the background, backing up some stuff. So I have stopped that, and hopefully my Wi-Fi is pretty decent at this point. Okay, so you guys should know I already graded the exams and all that stuff is updated. The key, well, not the key, but at least some of the solutions are on there. You go to the grade book and you can actually see the solutions in the actual grade book for some of the problems. At least the ones that I coded, you'll see the solutions in there. Today, we'll just continue on and finish out 7.1, and we'll step into 7.2, actually. So let's see, where did we leave off? Last week, we left off with this. We're still in the middle of by parts, and actually, we're in kind of the shallow waters of by parts method. There's actually a higher level by parts that we're about to get into, but the one we ended with last time was the integral of tangent inverse, or the arc tangent here, something that you do not know offhand the antiderivative of, and so you have to resort to new techniques. And so the new techniques would be by parts, and our choice with the by parts method was allowing u to equal the tan inverse, so its derivative would be 1 over 1 plus x squared dx. That is one of the most important derivatives and therefore antiderivatives in calculus. So you have to be up on that one. And then the derivative, or the dv, strangely is just the dx. And that often happens when you have a single term or a single factor or a single function within your integral. You often do end up, if you have to use by parts, with an interesting choice for u. U will be the function itself, and dv will just be the dx. And when you integrate that dx, you get an x. And remember, the by parts method is the integral of u dv is equal to u times v minus the integral of v du. And so u times v here would be x times the tangent inverse, so that's where we got that, and then minus v du. V times du would be x times 1 over x, x times 1 over 1 plus x squared, and then dx. That's this business right here. And then we reminded ourselves there's a couple ways you could do this. Actually, this one, there's only one real way to do this. It's with basically another u substitution. We did a w because u was being used. And then you get down to this beautiful result right here. I don't think this is very memorizable. I wouldn't memorize the integral or the antiderivative of tangent inverse. You can always rederive it if you need to. If you have a great memory, go ahead and memorize that if you want. But in general, it's not something that I would commit to memory. There are other ones that are more important that I would, and I'll tell you that as we move forward. All right, so let's hop into the last kind of chunk of material in integration by parts. And we are in the excellent exponentials area. And exponentials and trig functions specifically do not play well together. I taught you a trick last time when you're doing a by parts integration, and that was that table. I think I wrote it down. I wrote out a table. I said, oh, well, you can write a table like this, u and dv, and you would write down what you're choosing u to be here and what you're choosing dv to be there. And then you would take derivatives of u until it turned into 0. And you would integrate those dv's until that u turned into 0. And it gives you kind of a nice little pattern to follow. You don't have to use that trick. In fact, it's probably best not to always use that trick. But here's an example of a problem where that trick just won't work. Tricks are just that. They're tricks, and they don't always work. Integration by parts always works, at least when it can. However, tricks, like that little table tend to fall apart in extreme situations. And this is an extreme situation. The integral of e to the 3x times sine of x dx. Well, when you're looking at that, first of all, you should just think about all your previous techniques. Like, let's see, tactics. I'll write down again, tactics. If you think about it, well, first of all, you can't do a direct integration. So that's just out of the works. There's no way you could do that. The second question is, can you do maybe a U sub? And we can easily see, hopefully you can see this, but a U substitution is a terrible idea here. U sub would be very bad because if you let U equal, let's just pretend the sine, well, first of all, the derivative of that is not there, but also that doesn't really help me with this e to the 3x. So that is not a great idea. And if you try to let U equal e to the 3x, its derivative is not there, nor does it have anything to do with the sine. Actually, technically, e does have a lot to do with the sine, but we're not going to get into that. All right, so U substitution is out of the question. So I guess we're going to have to go with our only other tactic, which is by parts. And here is probably the deepest waters you'll see with a by parts method. If you choose to go with by parts, in this case, think about, of these two factors, I guess you'll call them, sine of x or e to the 3x, which one can you integrate? Well, you can integrate both of them, honestly. So if that's the case, if you can integrate both of them, then you ask yourself, well, which one would change forms if I started differentiating? So again, I wrote that down in a previous lecture. If you can integrate both of those factors, then what you want to really look at is which of those two would change forms into a completely different style of function if I start differentiating it. And the reality is neither will. If you choose to differentiate e to the 3x, it will always remain an exponential, no matter how many derivatives you take. And if you choose to differentiate the sine of x, it will always remain either a sine or a cosine, basically a trig function, no matter how many derivatives you take. So this is the most dangerous situation. Like, exactly what do you do? Well, all things being equal here, just make a choice. And in fact, all things are pretty much equal here. You can integrate both of those. You can differentiate them. They'll never change forms. So it doesn't really matter to me which you choose to differentiate and which you choose to integrate. I'd like somebody just to say what you would like U to be. There's no wrong answer. I suppose there would be a wrong answer if you said cotangent or something like that, but somebody just let me know what U should be. Okay, sine. Good. All right, so let's go ahead and start there. We'll say let U, actually, I don't even need to say let U. Let's just build our table, right? So U is equal to, and dv is equal to. So if U is going to be the sine of x, not a bad choice at all, then du will be the cosine of x. And I like that because if you were to integrate the sine of x, you have that negative cosine of x, and that's kind of a pain, honestly. And then therefore, if U was the sine, then dv would be e to the 3x dx. And now we take the antiderivative. Remember, that's just like an e to the 3x, but because it's a multiplication by 3 on that x, you're going to offset it with the division. And now we could say, great. Remember, this is supposed to be the integral of u dv, and that will break apart into uv minus the integral v du. Now, what I'm going to do is leave a little bit of space down below, and I'm going to start my integration a little bit below some white space here. So I'm going to go ahead and say my integral way down here, e to the 3x sine of x. You know that if I'm leaving some space, this is a bigger problem. So this is going to be u times v. So going back up to our work up here, it's going to be u times v. So 1/3 e to the 3x times sine of x. Let's write that in. 1/3 e to the 3x times the sine of x minus the integral of v du. Going back up to the top, the integral of the product of these two right here. Oh, and that should be, by the way, a dx on the back end. Sorry about that. So that's a 1/3 e to the 3x cosine of x dx. 1/3. I can at least bring the 1/3 out. 1/3 e to the 3x cosine of x dx. Again, I mentioned something in the previous lecture. When you make or when you use by parts, you do not want your second integral. So this is our original integral right here. You don't want the second integral, the integral of v du, to get more complicated. And this is not more complicated. It's actually just as complicated as the original integral. And so this does not break my rule of thumb. My rule of thumb was just don't allow that second integral to get worse. And it hasn't gotten worse. It's kind of remained, as far as complexity, about the same. So what do you do from here? Because you don't know how to integrate e to the 3x times the cosine of x dx. Well, you're stuck again, and you'll have to yet again run by parts. This is a double by parts. It does happen very commonly that you'll have a double by parts. And so let me go ahead up above in the space that I've reserved up here. I will go ahead and take a look at the integral. Whoops. Do this in blue ink. The integral e to the 3x cosine of x dx. Now, I mentioned again in a previous lecture that once you make a decision on what you're going to differentiate, stick with that decision. So if I end up having to run by parts yet again, which I do in blue ink here, I'm running by parts yet again. If that is the case, choose the same style of function for what's going to be u. In other words, here, when I do my by parts method, I'll just abuse notation a little bit. I'll put u in a dv here, even though technically they're different u's and different dv's. Actually, the dv is going to be the same, but the u is not. I'm still going to abuse the notation. I'll just use the u and dv. All right, so what I'm going to choose for u is the same style of function as I did before, the same trig function. And therefore, the dv is just going to be e to the 3x dx. There's a specific reason for that. If you choose the other way around, if you were to therefore say, no, you know what, I want that u to be e to the 3x, you're going to undo everything you just did. It's like you tied your shoe and then untied your shoe. You don't want to do that. You want to continue seeing what happens if you go down that path. Make the same choice again, basically. The derivative of that cosine is a negative sine of x dx. The antiderivative of e to the 3x is 1/3 e to the 3x. And so that blue ink, I'm going to substitute in for this integral right here. Probably most students actually do great with this material, with one simple arithmetic exception. They forget they have the 1/3 hanging out front. So be very aware when you substitute in what we're about to substitute in, that you have that 1/3 hanging out in front of that blue ink. Technically a negative 1/3. There we go. So let's go ahead and take a look at that integral. We're going to take u times v, which will be 1/3 e to the 3x cosine of x minus the integral of v du. And in this case, that'll be minus 1/3 e to the 3x sine of x dx. So it basically will become a plus. Again, 1/3 can be moved out front, and we have e to the 3x sine of x dx. Notice that we've done all this work and we've arrived at a format or a picture for this integral that involves the original integral. There's our original integral. So our original integral ends up being something involving our original integral. There's nothing wrong with that. If you do a little bit of distribution, you'll see something beautiful kind of happens here. So I'm going to go ahead and say this implies, I'm going to rewrite this whole thing. I'm going to say that implies the integral, of e to the 3x sine of x dx is equal to 1/3 e to the 3x sine of x minus 1/9 e to the 3x cosine of x minus 1/9, because I'm distributing this negative 1/3 through, minus 1/9 integral of e to the 3x sine of x dx. And this is just a rare style of problem. I should say it's uncommon. It's not rare, it's just uncommon. But where you have a picture that you're trying to solve for and it occurs on both sides. You've seen this in algebra when somebody says, hey, I have x is equal to some bunches of numbers plus 3x or something like that. You would just subtract 3x from both sides. You get negative 2x is equal to all that business and divide by negative 2. It's the same thing here. We're going to add 1/9 of that integral to both sides. Let me go ahead and erase all this stuff. So I'll add 1/9 of that integral to both sides to get 9/9 plus 1/9 is 10/9 of those integrals. That's equal to the right-hand side. I was just debating if I wanted to copy that or rewrite it, but I'll just rewrite it. And then you multiply both sides by 9/10. There's a little bit of a thing I'm missing here. I'll mention in the end. I'm going to multiply everything by 9/10. So we get our original integral, the integral of e to the 3x sine of x dx. We now know what that equals. It equals 9/10 times all this stuff. What is that? 3/10 e to the 3x. Yes, you can factor out the e to the 3x. I just didn't. Minus 1/10 e to the 3x cosine of x. And the thing I'm missing here is the plus c. It's an indefinite integral, so I should put the plus c on there. So this is kind of the worst case scenario when you're doing by parts, is that you end up having a product of two functions, both of which can be integrated. Let me go back up. Well, I'll just leave it like this. You can see it all on one page. Both of our original functions within our integral can be integrated, and when you differentiate either of them, they never change forms. They both retain either an exponential form or a trigonometric form. And because of that, it ends up invoking kind of the worst case scenario. You cannot do that little table I taught you last time because your derivatives will never turn to zero. So that table works beautifully when you have a polynomial times something. It's beautiful for that, but it's pretty much worthless for everything else. So the true integration by parts here ends up leaving you kind of with a little bit of algebraic work at the end, adding your integral to both sides and multiplying or dividing both sides by the coefficient of that. But a really great example. That's a style of example I put on quizzes or on exams, something like that. Take a drink here. Hold on. Okay, questions on that? Anything that I did in there that might have thrown you off? How do we know before we start the problem that we'll end up with the same integral? Yeah, generally speaking, you know that you're going to end up with the same integral if, when you're staring at your original integral, both of those pieces can be integrated, first of all. So sine and exponentials are integratable, or integrable if you want to call it that. Also, if each of those, when you differentiate them, will never change forms. It would be different if, for example, somebody said, I have the integral of x to the 10th e to the x dx. I know that I can integrate both of those pieces. Okay, so then I change gears and I say, well, which one do I choose to differentiate? I want the derivatives to eventually change forms. Well, the derivative of a polynomial will eventually change forms. So this one I know will eventually work out without me having to arrive at the integral of itself. So here's a case where you will not have the same integral show up on the right-hand side. However, anytime that you have e to the x mixed with a cosine or a sine of x, they both can be integrated and their derivatives never change forms. So this, you'll eventually end up with an integral, this same integral on the right-hand side. There is a little, not much of an exception, I should say, but just a kind of an issue. If it was like a secant of x times e to the x, while it is true that the derivative of secant always retains itself as a trig function, right? If you take its derivative, it becomes a secant tangent. You take another derivative, it's a product of trig functions. Another derivative, it's a product of trig functions, and so on and so forth. This is the exception to the rule because this guy right here, its derivatives just, not only do they not disappear, but they get worse, actually. If you try to take 3 derivatives of the secant, you'll see what I mean. It gets really, really gnarly. That's why you'll never see something like this. This you will not see because it's just terrible. It's a terrible, terrible integral. In fact, I don't think I've ever done that integral, and I don't want to. So, but in general, the rule of thumb is if it's a sine or a cosine times an exponential, you know you're going to get the same integral on the right-hand side. All right. Let's see. So that's actually all I had with that one. I kind of adjusted my my lecture notes slightly because I didn't want to have like 1,000 examples, basically. I know it's a massive over exaggeration, but I didn't, at some point I have to just say, well, I've given you all the tools. So I'm trying to remove a few examples here and there. But I try to keep in here the ones that are very academic, ones that can really give you some computing power. So we'll switch to the next subsection within 7.1, which is integration by parts, simply substituting. So I chose to name this subsection simply substituting, which I had just changed last night, by the way. So if it's not on your, if you printed out the lecture notes or something like that from last week, they're slightly different. Same examples, just slightly different. I call this simply substituting because you end up often thinking that you might need to use integration by parts, and you find out that a substitution is actually just easier. This one actually will still involve integration by parts, but let's just take a look at this integral. Let's say this was an exam or something like that, and you're asked to integrate this, right? The very first thing you should do is when I see a composition of functions, like an outer function, and then there's some function within it, like a natural log of 8x within that cosine, I immediately just knee-jerk reaction and think, I'm going to do a U sub. In fact, on your exam, right? On your exam, you had one that was, I think it was like tangent inverse of x to something power. I can't remember what it was. Okay. And that was to some power. And out here, there was a 2x, or it could have been something different. Doesn't really matter. 1 plus x to the fourth. This is a composition. Sorry, that power p should be something like 13. All right. This is a composition of functions. It's a 13th power, but inside that 13th power is a tan inverse. So I immediately, as a knee-jerk reaction, just say, I'm going to go ahead and let u equal that entire tan inverse that's inside that 13th power. And that ends up being an incredibly great substitution. So the same thing here. When I look at this integral of cosine of the natural log of 8x, I'm thinking to myself, that natural log of 8x, I'd like that to be the letter u. So I'm going to start this entire problem with a u substitution. I'm not going to call it u. I'm going to call it w, because I know you don't know it, or maybe you do, but I know that this is going to end up requiring by parts, and I want to save my letter u for that. So I'm going to let w, or happy face, whatever you want, equal the natural log of 8x. Then dw will be 1 over 8x, but by the chain rule, times 8, and then dx. So the 8's cancel, and it's just 1 over x dx. So that means, since we don't have a 1 over x dx to steal away, I'm going to go ahead and isolate the dx and say, wherever I see a dx, I'm going to trade it out for an x dw. Now, a lot of people will look at that and say, but we didn't have a 1 over x dx to steal, so isn't this a bad substitution? No, it's not a bad substitution. It just takes a little extra work, But this is going to be the integral of dx will be traded out for an x dw. And then cosine of, instead of the natural log of 8x, it's just w. It's almost completely in the world of w's. By the way, this is something to mention because on the exam, a few people ended up with an integral involving two different variables and they integrated. Completely illegal. You can't do that. Please do not. When you see an integral that involves multiple variables like this, you have to somehow get them all into the same world. The world you want to get them into is this one right here, dw, or the world of w. So let's go ahead and get that x into the world of w very easily because we have a relationship right here. I'll raise both sides base e, so e to the w is equal to 8x, and divide both sides by 8, and that implies that 1/8 e to the w is equal to x, and now we are actually back to what we just did. 1/8 integral, that x is going to be e to the w, well, the 1/8 is out front, cosine of w, dw. And this is literally the last example. Okay, it's not literally because it's not exactly the same, but it is very similar to the last example we did. It's a product of an exponential and a trig function. I know right ahead of time, before I even begin this problem, I know this is going to end up with an integral of e to the w cosine of w, right? This is going to expand out. So what I'm going to do, and I highly recommend that you do this, is I'm going to focus as an aside just on the integral of e to the w dw, or sorry, e to the w cosine of w dw. Sorry about that. In other words, I know there's a 1/8 multiplying all this. I'm going to wait until the very end to worry about that. It's just, I think, a good idea. Now, some people might disagree with me, but I think it's a good idea. All right, so this time I'm just going to show it the other way around. What if we had chosen in the last example to let u equal the exponential? Why not, right? Let's see, dv. Then dv would be the trig function. And du would be e to the w dw. And v would be the sine of w. And there's nothing wrong with that. It's going to be the same amount of work as it was in the last example. So this is going to be uv, which is e to the w, sine of w, minus the integral v du, which is going to be e to the w, sine of w, dw. And we again have to do by parts because it's still an integral of an exponential and trig function. I'll use blue for that. Again, I'm going to abuse notation here. Technically, we're using different letters, but whatever. This is just my in-between work. These are, if you do any type of programming, some people in here I know do some type of coding or programming. They're going to be computer science majors. You can think of these as local variables, u and dv and all that stuff. They're local to what I'm doing in the moment. All right. So let's see. I'm going to make the same choice for u. That's e to the w. And the same, therefore, my dv is going to be the sine of w dw. And here we go. Du obviously is e to the w dw. And v is going to be the negative cosine of w. Okay. That's the antiderivative of the sine. All right. So plugging that in to this, we have e to the w sine w minus, and then I'll use my blue ink here, u times v, which is a negative e to the w cosine of w, minus the integral v du. That's minus a negative, so I'll just put that positive in here. Integral of v du, cosine and e to the w. Okay. So we get that the original integral, not the original, but the original green integral right here, ends up being a sum statement involving itself. So let's go ahead and clean that up just a little bit. I don't need to do a ton of cleanup. And in fact, in this case, I'll go ahead, maybe down here, integral e to the w, cosine of w, dw. In those first two terms, this guy and this guy, this time I'll just factor out an e to the w. Why is it negative? Which part? This part right here? Negative e to the w. It's so this part right here is, yeah. Why is that part negative? So the question is, why is this blue ink here negative, and why is that integral positive? It's because when we did this blue ink, that blue ink here, by the way, is related to our biparts blue ink. Scrolling over right here. And when we did our biparts blue ink, it was based upon this picture. So when we looked at that picture, we said, okay, which one are we going to differentiate? Which one are we going to integrate? Since we chose to differentiate the exponential before, we'll stick with that choice. And you get e to the w, its derivative is just regular old e to the w. And then dv is sine of w, dw, the antiderivative of sine of w is the negative cosine of w. And so that's why v times u, or u times v, is negative e to the w cosine of w. And then that's this part right here. That's where that negative came from. And then normally you would say minus the integral of, right? So minus the integral of v du, but v has a negative in it. So I just pulled that negative out, became positive. That's all. Okay. All right. So moving all my scratchy paperwork out of the way. Now what I'm going to do, just to remind you where we were cleaning this side up. I'm going to go ahead and factor an e to the w out of both those. So I'm going to have an e to the w times the quantity sine of w plus cosine of w. Let me just write that down. Times the quantity sine of w plus cosine of w. It's just because I didn't do it last time, and it's nice to showcase that you have options, right? So again, that's just the negative distributing right there, becoming a positive, and then I factor out e to the w, sine of w plus cosine of w. Now, when I take this negative and distribute it over here, I'll have a minus e to integral of e to the w cosine of w. dw. And you see what we're trying to find the value of actually occurs on the right-hand side as well. We'll go ahead and add that to both sides. This implies that two of those integrals of e to the w, cosine of w, dw, will equal that e to the w times the quantity sine of w plus cosine of w. It's a lot of handwriting, honestly. And technically, there is a plus c that is going to happen. I just reserve that until the very end. Divide both sides by 2, and we will have the value of the integral. This is not the original integral, by the way, but it's close. And a piece of advice that I often forget to give is to pause, take a look at the problem, and ask yourself, wait, is there any issues that I have with this problem that are related to where I started? In other words, let's take a look at where we started. Doesn't look like the same problem at all, but that's because we did a W substitution. And so we have to go ahead and resub back in. And as Veronica just said, there's still a 1/8. Right? So if I zoom out a little bit, you'll see that we did all that work to find out what this value is, and we still have a 1/8 times that. So let's go ahead and we'll actually stay at the top here. And I'm going to go and move this stuff over so it's out of my way. just a little bit. Don't need it too far out of the way. And I'm going to go ahead and say this is equal to 1/8 times the quantity. Ooh, that's a weird quantity. Times the quantity. And now we have just found the value of integral of e to the w cosine of w dw. We found that to be 1/2 e to the w times the sum of the sine and the cosine. Let me go ahead and at least do that. 1/2 e to the w times the sine plus the cosine. Oops, sine of w, sorry. Remember, there is a constant of integration. I'm going to call this plus c sub 1. It's just a constant. I'm just kind of giving it a subscript on there for the time being. And now what I'll do is I'll not only distribute the 1/8 through to both of those terms, but I will also resubstitute back in what w was. W was the natural log of 8x. So distributing through and resubbing, I get 1/16 e to the natural log of 8x, which by the way is just 8x, and then times the quantity sine of the natural log of 8x plus the cosine of the natural log of 8x, and then plus 1/8 times this constant, which is just a brand new constant. Now, I'd love to say that's it, but honestly, e to the natural log of 8x is 8x. So if you don't mind, rather than me rewriting the whole silly thing, I'm going to grab that guy right here, move it down, and I'm going to just put in its place 8x. Obviously, 8x over 16 is x over 2. I'm just too lazy to write it out. But there you go. So there's a lot of work in this style of problem. Great rehash of what we just did a few moments ago, which is kind of a double by parts. You can see that these do creep in. Generally with U substitutions, they creep in quite often. So, and people were on their toes, making sure I had my 1/8 in there and all that fun stuff. So questions on this entire example, there's quite a bit going on in there, but questions on anything in there. And while you type, I'm going to mute so I can drink. And I'm back. All right. Well, if you do have a question, feel free. I'm just going to advance a page and see what we have next, just in case. Oh, it's a very nice definite integral. Again, the title that I gave to this subsection of material is simply substituting. And the reason why I'm calling it that is because it's my clue for you guys that really all I'm doing the entire time is looking for U substitutions if I can make my work a little bit easier. In this case, again, it's a composition of functions, a cosine composed with a square root. So it is almost immediate to me to make a U substitution. In fact, I will. U is equal to the square root of x. Now, there are other ways to do this problem. In fact, let me go ahead and showcase a kind of a neat way to do it. So a lot of people would do this. That implies that du is equal to 1 over 2 root x dx. And I think most people would kind of nod their heads and say, yep, that's exactly what I would do. Notice that we do not have a 1 over 2 root x to steal away. All we have is a dx. So I'm going to go ahead and isolate this dx. Dx is equal to root x and then times a du. So that's what I'm going to trade out a dx for. So this integral, this definite integral, will be traded out for a 2 root x du, and then we have a cosine of u. Now, I do want to change my limits of integration. I try my best to tell my students to do that, to always, when you're changing into a different world for a definite integral specifically, change your limits of integration as well. And that is because you don't have to change back to the world of x. with definite integrals. You can always stick within the world of u from this point forward. Just makes it a little bit easier. So if x were 5, well, then u is root 5. And if x were 10, well, u would be root 10. And there we go, root 5 to root 10. I'm not going to say it's beautiful. I'm just going to say that's what it is. Okay. But notice we still have a mixture of variables in there. This is an integral with respect to u, and yet I have an x in here. But luckily, the square root of x, I happen to know, is just u. So I'll go ahead and say this is the same thing as 2 times the integral from root 5 to root 10 of u cosine of u du. Notice this is a product of a polynomial and a trig function. So this one will not result in a function. It won't result in an integral involving itself. It only is like that when you have exponentials times trigs functions. And in fact, in this case, I'm going to use my little trig table. My trig table, normally I would write u and dv, but unfortunately, u is taken. I was silly enough to do that. So I'll write as v dw. It doesn't actually matter what the name is. I'll build my little table here and look at the pieces of these two pieces. You're going to differentiate one and integrate the other. The one you're going to choose to differentiate is the one that will disappear. So I'm going to let u be the thing I differentiate, and its derivative will be 1, and the derivative of that will be 0. Versus the antiderivative, my dw is going to, is going to be the cosine of u du. Oops, cosine of u. I'll just leave the du off there. It's the cosine of u. And when you anti-differentiate or take the antiderivative, you get the sine of u, and take the antiderivative of that, and you get the negative cosine of u. And you stop when you reach the same level as 0, basically. All right. And now I'm going to go ahead and use green and red ink to show my mindset here. You're going to add the product of those two and subtract the product of those two. Again, add, subtract. Here we go. It's going to equal 2 times. Don't forget that 2 is hanging out there. Add the product of u and sine of u. They're being evaluated from root 5 to root 10. And then subtract. I'll do the subtraction in red. In fact, I should have said the addition in green there. I'll subtract the product of 1 and negative cosine. Then if you think I was going to say subtract the integral, I've actually just evaluated the integral. So you don't have to worry about that when you use this little trig table. So we're going to subtract the product of 1 and negative cosine. So that's a negative cosine. Obviously, I could have just quickly said that's plus cosine when you do everything, but I'm just taking my time with it. And we're going to evaluate this from root 5 to, again, root 10. It's 2 on the outside. Plugging in root 10 here. Root 10, sine of root 10. And minus root 5, sine of root 5. You don't know what those are. That's exact form. Just leave it. And then remember, this is going to be a plus. So plus, plug in root 10, cosine of root 10. And then minus, plug in root 5, cosine of root 5. Again, this is exact form. You could just leave it just like this. Nothing wrong with that. And that would be the area underneath the cosine of root x from 5 to 10. Which we often forget about. We often forget that's exactly what we're doing, finding areas underneath curves. So anyhow, that table is a really cool way of doing this problem, though. Sorry, I had to have some chai. So if you have questions on that, please let me know. Now I'm going to move or step a little bit forward here into synthesis questions, which is kind of like grabbing things from the past and including it in what we're doing now. Do we need a plus C? That's a great question. Do we need a plus C? So the only time that your integral needs a plus C is if it's an indefinite integral. In other words, you don't have limits. If you don't have limits on your integral, then you need a plus C. But when you have limits, you're found the exact value. It's not the, basically what we're saying is the exact area underneath this curve from 5 to 10 is this number, whatever that number is. It's not, we're not off by a constant. That is literally the area underneath that curve. You only need the plus C when you're doing indefinite integrals like this, because nobody told us what the limits are. We're going to say the antiderivative is x squared over 2 plus some constant. And the reason why is because, remember, this is the antiderivative. The derivative of that should always turn into the integrand. And if you take the derivative of x squared over 2, it's definitely x. If you take the derivative of a constant, it's definitely 0. So x plus 0 is x. So this is the true antiderivative right here for an indefinite integral. But for definite integrals, that plus C is not there. Okay. Perfect. And the synthesis question. Oh, sorry. I just saw a new message. So the table part, somebody's asking about the table. Like the table, first of all, the letters are a little confusing. Let's pretend as though instead that the integral wasn't in terms of u. Let's just say that it was the integral of 2x cosine of x, just for the moment, dx. Okay. Normally, you'd say I want to choose something to differentiate and something to integrate, right? And then you do by parts, and you totally could. Nothing wrong with that. However, the table automates quite a bit of this. And so if you do the table, you can say, okay, the piece that I want to differentiate is x, and the piece that I want to integrate is the cosine of x. Now, if you think about it, when you're running the by parts method, you're choosing a u and a dv, and you're going to take the derivative of u. Well, the derivative of u is literally just 1. And you're going to integrate dv. Well, the integral of dv is just the sine of x. So the table that I'm doing is speeding things up a little bit. However, most people say, well, then I stop right there, right? Not really, because when you integrate something u dv, you end up with a u times v, this times this, minus the integral of v du, the integral of, again, this, but times this. But we haven't actually computed the integral of v du yet. Well, I'd like to. And it turns out if you go one more line here, take one more derivative to where this is 0, take one more integral, antiderivative, to where this is negative cosine of x, what you have actually done, if you take a look at this is the integral of v du. Notice du is 1 and v is sine, and the integral of sine times 1 is going to be the negative cosine. And so that's where that comes from. That's how the table automates it quite a bit, actually. And then because there's this alternating pattern with this plus or minus sign here, well, it's the positive product of u and v, and then minus the integral v du. And so that's why it alternates. And the table alternates forever like that. So it's, if I put the lecture, the video for the lecture up in our folders on My Open Math. So from last class. So take a look at that. It actually, I do one, I think I have a 4th power, a 3rd power of x on that. And that one showcases how that table works really nicely, actually. It works really well. All right. So the synthesis question, compute the volume generated by rotating the region underneath natural log of x from x equals 1 to x equals e about the x-axis using shells. This will happen. Calc 2 is so dense that I like to make sure that we revisit old information often so that by the time you get to the final exam, you're totally well prepared. You don't have to like review a ton of old stuff. You'll be solid with that. So here is the natural log graph, if you were to look at it, but I don't need all of that stuff. I'm really going from x equals 1, which is, whoops, x equals 1 to x equals e. Remember, the natural log of 1 is 0. Natural log of e is actually 1. That's what that height is right there, e comma 1. And we want to rotate this about the x-axis to create a solid. Looks like this. Okay. But they're forcing our hand. They're telling us that we have to use shells. So if I'm going to use shells and I'm rotating about the x-axis, visually I know I'm doing horizontal slices here of thickness delta y. And the volume of that shell when it rotates around, which I'm just sloppily doing it. Okay. Good enough. That's actually not too terrible. The volume of that shell, when you rotate that around, is going to be the circumference, 2 pi r, times the height, which is essentially this length right here, times its thickness. And now we go ahead and step through each of these, 2 pi. The radius of the revolution, right? This radius right here is y top minus y bottom. I'll even write that in there. Y top minus y bottom. Most people did exceptionally well on the exam with that. I was super happy. The height, quote unquote, is this distance right here. That's x right minus x left. And then you have a thickness, and we already labeled that delta y. So I'm going to say delta y there. 2 pi. Y top, well, this y top is just y, whatever that y value is. So I'm going to call that y sub I. Y bottom is 0. That's to the axis of rotation. And then x right, the right edge of this slice is e. The left edge of this slice is defined by the curve. And the curve is y equals a natural log of x. Well, I need to solve that for x. That's the same thing as e to the y is equal to x. So our left edge there is e to the y. And then we have delta y. And so now we can go ahead and run the integral. The true volume is going to be 2 pi. The integral y, we're going to start stacking slices at a height of 0. We'll end stacking at a height of e. Nope, height of 1. Actually, I think it's height of 1 is where we stop. Sorry about that. And then y times e minus e to the y dy. This is in this section because if you distribute that y, you'll figure out very quickly you need by parts. So I'm going to use a different ink here. This is 2 pi, integral from 0 to 1 of y times e. Let's call that y times e. E is just a constant, so think of it as 2y or something like that. Minus y e to the y dy. Again, e is a constant. Don't let that fool you. That's generally a point of confusion for people. 2 pi e, integral from 0 to 1 of y dy, minus 2 pi, integral from 0 to 1 of y e to the y dy. And we know the first integral is just going to be y squared over 2, evaluated from 0 to 1. The second integral I'm going to leave alone for the time being because I want to talk about it. So let's go ahead and evaluate that first one. Just becomes 1 times pi e. So it's pi times e minus 2 pi, integral from 0 to 1, y e to the y dy. Now we got to this point right here. And the reason why I want to spend a moment talking about that integral is because that's probably one of the most important, or popular, I should say, integrals in differential equations. So if you guys are moving through engineering or physics or anything, really, you're probably going to have to take differential equations. And this integral, x e to the x, we'll just call it, that happens all the time. So the value, what this turns into, is it's almost advisable just to memorize it. You'll figure out very quickly it's very fast to do, but we're going to go ahead and derive it, and then I'll just tell you it's a good idea to memorize its value. Give me a moment. I'm having a chai. Okay, so let's see. Where did the 2 and the 2 pi go at the beginning? Oh, it's because when I integrated the y, it became a y squared over 2. Oops, except you don't want to write in the highlighter. So it became a y squared over 2, and there was a 2 sitting out there. I just canceled them. Yep. Now let's focus in on that y e to the y. And in fact, because it's so important and it's often written differently, I'm just going to write it as x e to the x. The integral of x e to the x dx. Sorry, that's my phone. Everybody's probably like, wait, whose phone is that? It's my phone. X e to the x. All right, so let's go ahead and do by parts. This is obviously a by parts method, right? And in this case, I'm going to go ahead and do the u dv table. The thing we'll differentiate is the x. The thing we'll integrate is e to the x. Well, the derivative of x is 1, and its next derivative is 0. And the integrals of e to the x are super nice. Okay. Remember, the first diagonal, it's always an addition. The second diagonal is always a subtraction, and it alternates thereafter. And so we can see very quickly that this integrates to become a positive x e to the x minus 1 times e to the x. And then there is a plus c on there technically. But this is a very, very powerful thing to remember, a very powerful integral to remember. So if you can remember that, that happens all the time. That specific integral happens so often, it's probably a good idea to just put it in your memory banks and leave it there. I'm going to use that integral very quickly down here so that we know this is 2 pi e, or I'm sorry, pi e minus 2 pi times y e to the y minus e to the y, evaluated from 0 to 1. And now I can just plug that stuff in. Pi e minus 2 pi. Plugging 1 in, we'll get e to the first minus e to the first. Kind of nice. And then plugging 0 in with minus signs, so you're going to flip all the signs here. You have minus 0 and then plus e to the 0th. That's e to the 0th, by the way. E to the 0th. And so when you simplify this all out, that's just going to be pi e minus 2 pi. That is the volume of that rotation. E to the first minus, yep. Something as an aside that I could easily ask maybe for a quiz or an exam or something like that is to compute the integral of, let's say, x to the 4th e to the x dx. You are more than welcome to use the trick because that will be very powerful here. U versus dv. Pick something that you want to differentiate. Obviously, the x to the 4th, because that will definitely disappear in the long run, and start differentiating. 4x to the 3rd, 12x squared, 24x, 24, and then 0. And the thing you're going to integrate, well, start integrating. Luckily, it's just e. And then you draw those green and red lines. I use green and red just because I can, but make sure I use green and red because green to me means positive and red means negative. And you just alternate back and forth between them. I'll just do it like this so that I can speed it up. And so very, very quickly, if you use that trick, you get a positive x to the fourth e to the x minus 4x cubed e to the x plus 12x squared e to the x minus 24x e to the x plus 24 e to the x. And don't forget there is a plus c at the end of that. Yeah, it does. This little trick here, it works no matter how ugly your integrand is. If it has coefficients and ugliness and it's not just x to the fourth, it could be x to the fourth plus pi x squared minus e or something like that. It would still work out. The only time it doesn't work is when you have very special scenarios, like specifically if it's not a polynomial times something. Polynomial times exponential or a polynomial times a trigonometric function, it works beautifully. But it doesn't work if it's a trig times exponential. Yeah. A really cool way of doing it, by the way. I never taught that in the past, but I just decided I'll just go ahead and teach it just because it's kind of a neat little trick and it speeds things up. And the last example that we have in this section is more for my benefit because I like this stuff. So, and I suppose for yours as well, you've seen problems sort of like this on a homework where they don't tell you the functions, but they give you a picture and they say, tell me something about this. My Calc 1 students see this all the time. So approximate the area underneath the curve x g double prime from 0 to 2 if g is that function graphed to the right. So taking a look at this integral, the integral from 0 to 2 of x g double prime of x dx, you look at that and you think, I don't know what to do. I mean, am I supposed to maybe take two derivatives of this, or what am I supposed to do, right? You just have no clue. Note that this is the product, actually, of two functions. It's the product of x and then a different function. So I could use by parts here, and in fact, I'm going to. I'll go ahead and I'm not going to use the table. I'm actually going to just set it up like we would normally do that. I'm going to say I'll let u equal x because I can differentiate that, and I'll let dv equal the piece I can integrate. I can actually integrate a g double prime of x dx. It'll become a g prime of x. That's all. The integral of g double prime is g prime. So that's going to be pretty easy. Du is just going to be a dx. Again, the antiderivative of g double prime is g prime. And so we know that this integral will become u times v, which is x times g prime of x. By the way, that's evaluated from 0 to 2, minus the integral v du, g prime of x dx. And again, that's from 0 to 2. And you look at that and you say, but I wasn't given the picture of g prime, so what am I supposed to do? Well, remember, the fundamental theorem of calculus tells us the integral of g prime, that's just g. The antiderivative of g prime is just g. So this picture, I'll substitute, it's 2 times g prime of 2 minus 0 times g, oops, that was supposed to be a 2 there. Minus 0 times g prime at 0. Okay, so that's just this first piece right here. Minus the integral of the derivative. Well, that's just going to be g evaluated at 2 minus g evaluated at 0 by the fundamental theorem of calculus, technically part 2. So let's go ahead and see if we can figure this out. Well, I know 0 times g prime, that's gone. I don't have to worry about that. The question is, what is the slope of this curve? Because this is g right here. What is the slope at time 2? What is the slope of this curve at time 2? And if you look at that curve, it's basically got a slope of 1. It rises 1 and runs 1, roughly. Yeah, exactly. So g prime of 2 is approximately 1 minus g of 2 plus g of 0. Well, that's going to be 2 times minus g of 2. Well, g of 2, it looks to be about 2. G of 0 looks to be about a 0.4. So without even knowing the function, just being given the graph of the function, I can still answer this question. It's a really good problem. That's why I call it synthesis questions, because it involves a lot of stuff from the past. Like, you have to remember that the fundamental theorem of calculus, that the integral of a derivative returns the parent function. The integral of g prime will just return g. You also need to remember that g prime is just the slope of this function at that point. Does the trick work here? Nah. I mean, you could write it out. It's not really going to super help you here, because it's, you would have u versus dv. You're going to obviously differentiate u. dv is g double prime, right? And so integral is g prime, and this is g. I guess you could, right? It kind of does work. So x times g prime minus g. Yeah, you could. Yeah. Absolutely. It's x times g prime minus g. And remember, you're evaluating all this from 0 to 2. So it would be 2 times g prime of 2, which is exactly what we had, minus 0 times g prime of 0, which is exactly what we had, minus g of 2, and then plus g of 0, which is what we had. Yeah, the trick kind of does work here. All right, so that's pretty much everything you possibly can squeeze out of the by parts method.